This is Lesson 9 in our Calculus 1 series, the derivative function. In Lesson 8, we saw the derivative of f at the point x equals a, and we saw that all of these expressions mean the same thing. We have f prime of a is equal to the limit as h goes to 0 of f of a plus h minus f of a over h. We could also take that limit as limit x goes to a of f of x minus f of a over x minus a. We know that this offers the slope of f at x equals a, which is the same as the slope of the tangent line to f at x equals a. This is called the derivative of f at x equals a, and also can be thought of as the instantaneous rate of change of f at x equals a. In this lesson, instead of specifying a point x equals a, we leave x in the computation to represent any x value. So here we're looking at f prime of x, which is the limit as h goes to 0, f of x plus h minus f of x over h. And so our result is going to be a function of x, and this is the derivative function f prime of x. And so similar to the list of expressions that are equivalent we saw above, we have this shorter list of equivalent expressions. We have f prime of x is the limit as h goes to 0, f of x plus h minus f of x over h. This is known as the definition of the derivative. We know that this is the slope function for f of x, also called the derivative of f of x, or the derivative function for f of x. So let's take a look at an example. Here we have f of x equals x to the third minus x squared minus x plus 1. Let's find f prime of x and use it to find the slope of f at these three x values. So we're asked to find f prime of x, so we set up our limit definition of the derivative. F prime of x is equal to the limit as h goes to 0, f of x plus h minus f of x over h. F of x plus h means we're plugging x plus h in for each of these x's here. So that's going to give us x plus h to the third minus x plus h squared minus x plus h plus 1. And here we're subtracting off f of x. Don't forget to use parentheses here or distribute that negative through each term of f. And this is all over h. So we have a little bit of expanding to do in the numerator before we can simplify. So multiplying out x plus h quantities squared, we're here, x squared plus 2xh plus h squared. For x plus h to the third, we need to multiply in another factor of x plus h. And so doing that gives us x to the third plus 3x squared h plus 3xh squared plus h to the third. And so now we're ready to plug into our formula. We have x plus h to the third minus x plus h squared. Notice I distributed the negative sign here. Minus an x plus h, again distributed the negative sign. And this is minus f of x. And again we've distributed the negative sign. And at this point we could do a whole bunch of canceling. We have positive x to the third, negative x to the third, negative x squared, positive x squared, negative x, positive x, plus 1, minus 1. And notice that everything remaining in the numerator has a factor of h, and that is what we're looking for. So that we can factor out an h from the numerator and cancel it with the h in the denominator. And so what we're left with here is limit as h goes to 0, 3x squared plus 3xh plus h squared minus 2x minus h minus 1. And at this point we can just plug in h equals 0 to take the limit. And so we're left with 3x squared minus 2x minus 1. And so this is our derivative function f prime of x. So for the original function f of x equals x to the third minus x squared minus x plus 1, our derivative function is f prime of x, that's 3x squared minus 2x minus 1. And again, this is the slope function for f of x. So that means we could use it to find the slope of the original function f at particular x values. And so we were asked to compute the slope at x equals -1, x equals 0, and x equals 2. So let's do that here using f prime. F prime of -1 is 3 times -1 squared minus 2 times -1 minus 1. That gives us a 4. And so the slope of f of x at x equals -1 is equal to 4. At x equals 0, the slope of f is given by f prime of 0, and that's just -1. And at x equals 2, the slope of f is given by f prime of 2, and that's 7. So if we take a look at the graph of the original function, f of x, we can note on the graph the slopes that we just found. We found that at x equals -1, the slope of f is equal to 4. At x equals 0, the slope of f is equal to -1. At x equals 2, the slope of f is equal to 7. And keep in mind that in Lesson 8, if we wanted to find these three slopes, we would have had to take 3 limit computations. But now we can do the limit computation once with x holding the place of any x value, and then plug in the different x values. So it's a bit more efficient. Now also, let's compare this original f of x to the graph of its derivative on the same set of axes. So here's the original function f of x, and here is its derivative f prime of x on the same set of axes. So let's see what we found. We found that the slope here we said was equal to 4. Well, notice the y value on the derivative function f prime is equal to 4. This is saying f prime of -1 equals 4. Here at x equals 0, we found the slope of the original function to be -1. And on f prime, the y value for x equals 0 is -1. This is saying f prime of 0 is equal to -1. And at x equals 2, for the original function, we found that the slope is equal to 7. And on f prime, the y value is in fact equal to 7. So f prime of 2 is equal to 7. So the y values on f prime are giving the slope values on f for any given x value. And it's worth noting a couple of other x values here that are going to be helpful for us in the future. Let's take a look at this x value. Our slope of the original is equal to 0. So notice the derivative function has a y value of 0. Also, at x equals 1, the slope of the original function is equal to 0, and so the y value of the derivative function is equal to 0. So reading off information like this allows us to even start with a sketch of an original function and make a sketch of the derivative just by looking at the different slope values along the curve. Let's take a look at another example. Find f prime of x using the definition of the derivative, and f of x is equal to 4 minus radical x. So the definition of the derivative is this limit definition here, so we start out writing f prime of x is equal to limit as h goes to 0, f of x plus h minus f of x over h. And so we want to plug x plus h into our function here. And so that's going to be 4 minus radical x plus h. And then we subtract off f of x, again, use parentheses here, and that's all over h. So simplifying in the numerator, we see that the 4 and the -4 will cancel, and we end up with radical x minus radical x plus h over h. In order to be able to factor and cancel an h from numerator and denominator, we're going to have to get this h outside of the radical, which means, as we've seen in previous lessons, we're going to need to multiply here by the conjugate. So we have radical x now plus radical x plus h over itself. And multiplying through the numerator, we're going to get our first terms multiply to x. Our inside and outside terms are going to cancel, and our last terms multiply to a negative quantity x plus h. And in our denominator, we'll keep things factored. We have an h outside of the radical x plus h. Simplifying the numerator, we see that we're left with a negative h. And that's great, so we can cancel that h with the h in the denominator. And so we're left with limit as h goes to 0, negative 1 over radical x plus h. After we cancel the h, we know that we can plug in h equals 0 to take the limit. And so this is negative 1 over radical x plus radical x, or negative 1 over 2 radical x. So for f of x equals 4 minus radical x, this is our original function, we now know the derivative function f prime of x is equal to negative 1 over 2 radical x. Let's take a look at another. Find g prime of x using the definition of the derivative. For g of x equals x over x minus 2. So this is going to work the same way. You're going to start out setting up g prime of x is equal to limit h goes to 0, g of x plus h minus g of x over h, and then you'll compute from there. So please pause the video and work on that. So here we've set up our limit definition of the derivative. Plugging in x plus h into g, we have x plus h over x plus h minus 2. So we're here. And subtracting off g of x. Now we know we need to simplify this before we can plug in h equals 0. If we plugged h equals 0 in now, we would just get 0 over 0. So let's combine our numerator into one fraction. So that means we need to multiply x plus h over x plus h minus 2 by x minus 2 over x minus 2. And the x over x minus 2 gets multiplied by x plus h minus 2 over x plus h minus 2, so we can have a common denominator in this numerator. So combining our numerators, we have x plus h times x minus 2 minus x times x plus h minus 2. And dividing by h, we know that's multiplying by 1 over h, so that h can go into this denominator. And so we're here. Let's multiply out in our numerator so we can simplify. We have x squared plus hx minus 2x minus 2h, and then minus x squared minus xh plus 2x. And so we're here. We see our x squareds cancel, our 2x's cancel, and even the hx and xh will cancel additively. And we're left with just negative 2h over x plus h minus 2 times x minus 2 times h. And so we can cancel a factor of h, and at this point we can plug in h equals 0. And so we have negative 2 over x minus 2 times x minus 2, or a better way to write that, negative 2 over x minus 2 quantity squared. And this is our g prime of x. Now let's talk about some derivative notation. So we've been calling our derivative here f prime of x so far, but that's not the only notation you might see for your derivative. For y equals f of x, we can denote the derivative function by f prime of x, or y prime, or sometimes we see dy dx, or df dx. In these notations, I like to think of this as the slope. We've seen for slope delta y over delta x, change in y over change in x. This is very similar notation to that, dy over dx, df over dx. So in the next lesson, when we start doing a lot more computations for derivatives, we're going to be using these notations interchangeably. In this lesson, though, I'm using mostly f prime of x. Also note that we have the differential operator d over dx. So you'll see d over dx, and there'll be some function here inside the parentheses. And this means the derivative of whatever's in the parentheses with respect to x. And again, we'll see this much more in the next lesson. When evaluating at a particular point x equals a, we've seen so far that looks like f prime of a. We could also write that as y prime of a, or use an evaluation bar for these two notations. So this is saying this is dy dx evaluated at x equals a, or df dx evaluated at x equals a. And so for the function we looked at above with f of x equals 4 minus radical x, we found f prime of x to be negative 1 over 2 radical x. So we could also write y prime is equal to negative 1 over 2 radical x, or dy dx is equal to negative 1 over 2 radical x, or df dx is equal to negative 1 over 2 radical x. They all mean the same thing. And evaluating at a particular point, say evaluating at x equals 1, we could say f prime of 1 is equal to negative 1/2, or y prime of 1 is equal to negative 1/2. Or we could use the evaluation bar for these two. We would have dy dx at x equals 1 is equal to negative 1/2, or df dx at x equals 1 is equal to negative 1/2. And so again, in the next lesson, we're going to be doing lots of shortcut calculations for derivatives, and so we'll be using these notations much more. But let's continue on here. Let's talk about a function f being differentiable. A function f is differentiable at x equals a if f prime of a exists. And f of x is differentiable on the interval ab if f prime exists for every x value in the interval ab. So let's talk about this idea of f prime of a existing. What does it mean for f prime of a to exist or for it not to exist? Well, we know that f prime of a is the limit as h goes to 0, f of a plus h minus f of a over h. So for this to not exist means the limit does not exist. And this limit can fail to exist if the limit is infinite, and in that case our function would have a vertical tangent line, the slope would be infinite. This limit could also fail to exist if the left and right limits are not equal. And we're going to see a couple of examples of that where f has a corner point or a discontinuity at x equals a. So let's take a look at this example here. Here we have f of x equals x to the 1/3 power. And at x equals 0, we can see that the slope is infinite. So f prime of 0 does not exist, and f is not differentiable at x equals 0. And so in this case, f is differentiable on negative infinity to 0, union 0 to infinity. And these are open intervals on 0. Here we have f of x equals absolute value of x. And we note that for all negative x values, the slope of this graph is equal to negative 1, because this is the line y equals negative x. And for all positive x values, the slope of this graph is equal to 1, because this is y equals x. But what happens at x equals 0? At x equals 0, the slope from the left is equal to negative 1. The slope from the right is equal to positive 1. So the slope computation, the two-sided limit here, would not exist. And so f prime of 0 does not exist, and f is not differentiable at x equals 0. So again, f is differentiable on the interval negative infinity to 0, union 0 to infinity. Let's also take a look at this function here with a discontinuity at x equals a. And I've particularly drawn this graph so that it looks like the slope here is equal to the slope here. And so you might be wondering, well, then wouldn't the left slope equal the right slope, and wouldn't the derivative exist at that point? Well, we have to be careful with this computation for the limit definition. notice that the limit definition uses f of a. So as we're taking the limit as h goes to 0 from the left, we're talking about h values that are negative, and so a plus h would be to the left of a, and we would be taking slopes like this, secant slopes like this. And because this function is continuous from the left, we would get a finite limit here, whatever that slope would be. We would get that from our left-sided limit computation for the derivative. However, for the right-sided limit, we still have to use f of a. And so we're not taking secant slopes through this open circle. We are taking secant slopes through the function evaluation. And so as h goes to 0 from the right, we're approaching an infinite slope here from the right. Again, that's because we need to use f of a in this limit computation. And so we're not taking a secant slope with the open circle, we have to use this one. And so this is going to give us an infinite limit as h goes to 0 from the right. And so f prime of a does not exist as a real number, and then f is not differentiable at x equals a. And that's going to happen at any kind of discontinuity you come across. So if f is not continuous at x equals a, it's not differentiable either at x equals a. And so that tells us differentiability implies continuity. If f is differentiable at x equals a, then it must be continuous at x equals a. Now let's take a look at this graph and let's state the intervals on which the function is differentiable. So what are we looking out for? We're looking out for discontinuities, we're looking out for infinite slopes, and we're looking out for corner points, because these are going to be the x values at which the function is not differentiable. So let's start at the left and see what we have here. Here, at x equals -7, we have an infinite slope. So that tells us that f is not differentiable at -7. So f prime of -7 does not exist. At x equals -5, we have a discontinuity. So f prime of -5 does not exist. Here, at x equals -3, we have an infinite discontinuity. But beyond that, the function's not even defined at x equals -3. So if the function's not defined there, certainly we can't even talk about a derivative being defined there. So f prime of -3 also does not exist. Now here, at somewhere around -1.5, we have a 0 slope, but that's okay. And then over by x equals 2, we have a corner point. And so f prime of 2 does not exist. So we're asked to state the intervals on which the function is differentiable. So let's start at -infinity. And we're going to -7, open on -7, union -7 to -5, union -5 to -3, union -3 to 2, union 2 to infinity. And this is where f is differentiable. Now, I often see students confuse differentiability with continuity. So let's also state the intervals on which this graph is continuous. Now remember, intuitively, continuous means you can draw the graph without lifting up your pen. So the only discontinuities we have here would be at x equals -5 and at x equals -3. Everywhere else, the function is continuous. Not necessarily differentiable, but continuous. So for continuity, we only have discontinuities at x equals -5 and x equals -3. So those intervals look like -infinity to -5, union negative 5 to negative 3, union negative 3 to infinity. And so these are the intervals on which the function is continuous. But remember, differentiability, not only do we look out for discontinuities, we also have to look out for infinite slopes and corner points. Now let's take a look at higher order derivatives. If f prime of x is also a differentiable function, we can take its derivative, and that would be f double prime of x. So f double prime of x is the slope function for f prime of x. And as compared to the original f of x, f double prime offers the rate of change of the slope of f, which gives us information about the curvature or concavity of f. And we're going to see more about that in later lessons. But also note, if f of t is a distance function, we saw in the last lesson that f prime gave us velocity, so f prime of t is the corresponding velocity function. And in this case, f double prime of t is the corresponding acceleration function. For the example we saw above with f of x equals x to the third minus x squared minus x plus 1, we found that f prime of x is equal to 3x squared minus 2x minus 1. And so we can compute f double prime of x by taking the limit as h goes to 0, f prime of x plus h minus f prime of x over h. And so let's plug in x plus h into f prime. That's 3x plus h squared minus 2x plus h minus 1. And then we can subtract off f prime. Don't forget to use parentheses. We can expand our x plus h squared and multiply through that 3. Also multiply through this negative 2 and this negative here. And so here we can cancel 3x squared and negative 3x squared, negative 2x plus 2x, negative 1, positive 1. And what we're left with is 6xh plus 3h squared minus 2h over h. So we can factor out that h in the numerator, cancel that, and then plug in h equals 0 to take the limit. And so we get 6x minus 2 is equal to f double prime of x. So for the original function, f of x equals x to the third minus x squared minus x plus 1, we found that f prime is equal to 3x squared minus 2x minus 1. And remember, f prime gives us the slope of f at any given x value. Now we also found f double prime of x. That's 6x minus 2. That gives us the slope of f prime at any x value. And later in the course, we'll see that this offers also concavity information about f of x. Now let's take a look at the notation for higher order derivatives. We said above that for y equals f of x, we have the first derivative, f prime of x, y prime, dy dx, df dx. So similarly, we could talk about the second derivative, f double prime of x, y double prime, d square y over dx square, d square f over dx square. So in these two notations, we're applying the differential operator twice to y or twice to f. And so it looks like that. And of course, we could also talk about a third derivative, f triple prime of x, or y triple prime. We're using the differential operator 3 times here. And in general, the nth derivative would have notation f with parentheses around the n here of x. Same thing here, y, we would have parentheses around the superscript n here. And here we're using the differential operator n times. And I just want to point out the difference when you use the parentheses and when you're not using parentheses around a number. So f with the superscript of parentheses 2 of x, that denotes f double prime of x. That's the second derivative. But that's different than just writing f squared of x, because that means f of x quantity squared. So when you're writing down your higher order derivatives, you really want to be sure to use the parentheses if you're not using the prime notation to denote that it is, in fact, a derivative and not a power of the function. So in this lesson, instead of computing derivatives at a particular point, we're computing the derivative function for f. And still, it's a bit of work. We're using limits, but you'll see in the next lesson that we have a whole bunch of shortcuts we can use so that we're not computing the limit definition every time we need a derivative. And with this, we'll conclude our lesson on the derivative function.